Here's the video lesson for Practice Test C, Objective 2, to calculate stoichiometric quantities from balanced equations in terms of moles, mass, particles, and volume. We will be referring to the stoichiometry roadmap along the way, where we divide, ratio, multiply with 3 steps in our stoichiometry map. We begin by reading through our equation. Write the equation for the formation of magnesium phosphide from its elements. We want to form magnesium phosphide. Magnesium, who carries a +2, phosphide, who's a -3, so when we crisscross we get Mg3P2. The elements that it's built from would be magnesium and phosphorus. In a combination pattern, a metal to a nonmetal hooked by charge, we called that helpful hint number 1. And then to balance, we'll place a 3 in front of the Mg and a 2 in front of the phosphorus. A 3 to 2 to 1 stoichiometric ratio. Question 2. How many moles of magnesium are needed to form 3.5 moles of magnesium phosphide? Given a mole, calculate a mole. We call that a mole-mole problem. I begin by writing my number, 3.5. The unit is a mole, and of what? The label here, magnesium phosphide. We want over given in the stoichiometric ratio, the heart of our problem. It's a 1 parenthesis problem moving from the left to the right of our middle of the mole map, want over given ratio, where our target is moles of Mg. What we know from the balanced equation is that 3 moles of magnesium are required in every 1 mole of Mg3P2. The stoichiometric ratio of 3/1 shows the want over given ratio. In a 1-step mole to mole ratio, we would calculate 3.5 times 3 gives me 10.5 moles of Mg. In our third problem, how many grams of phosphorus are necessary to produce 68.3 grams of magnesium phosphide? We always begin by writing our number, 68.3. The unit after it is a gram unit, and the label is magnesium phosphide, Mg3P2. To go from a mass problem, we know to use 3 sets of parentheses. Where we divide, ratio, multiply, the middle parenthesis will be the heart of our problem, our want over given ratio. I like to get my 3 parentheses ready so I can see the target. I want to get to grams of phosphorus. Given a mass, calculate a mass with 3 steps to stoichiometry. In our first parenthesis, we'll need to convert the magnesium phosphide into a mole unit. We'll need the molar mass of Mg3P2. Magnesium, who has an atomic weight of 24.3 times 3, plus phosphorus, who has an atomic weight of 31, but I see 2 of them. 24.3 times 3 added to 31 times 2 gives me a molar mass of 134.9 grams in every 1 mole of Mg3P2. In the heart of our problem, we pull from the coefficients from our balanced equation. We want the phosphorus. Its coefficient is a 2. 2 moles of P go on the top. Starting from the product, where its coefficient is a 1. 1 mole of Mg3P2. We have a 2 to 1 stoichiometric ratio, our want over given. In the last step, since we want to land at a gram, we will take 31, the atomic weight of phosphorus, in every 1 mole of phosphorus. Divide, ratio, multiply, the 3 steps in our stoichiometry roadmap. Let me hit for us. 68.3 divided by 134.9 times 2 times 31. I get 31.39 grams of phosphorus. Our next question. How many atoms of phosphorus are necessary to react completely with 238 grams of magnesium? Given a mass, we want to go to the number of atoms. Begin by writing the number, 238. The unit after it is a gram, and the label is magnesium. The 3 steps to stoichiometry I like to get those set so I can see the target. What do we want to find? It's asking us to find atoms of phosphorus. I like to get that ready so I can see where I'm going. In our first conversion, 1 mole of magnesium set over its atomic weight, 24.3 grams, will convert our gram unit into a mole unit. In the heart of our problem, the want over given. We want to know phosphorus. Its coefficient is a 2. From the magnesium, its coefficient is a 3. We have a 2 to 3 stoichiometric ratio. The heart of our problem is want over given. In the last step, we want to count the number of atoms. To count individual particles, we use Avogadro's number. We know that there are 6.02 times 10 to the 23rd atoms of phosphorus in every 1 mole of phosphorus. To hit, we would start by hitting 238 divided by 24.3 times 2 divided by 3 times 6.02 E23. I find 3.93 times 10 to the 24th atoms of phosphorus. One more. How many atoms of magnesium are necessary to produce 9.3 times 10 to the 25th formula units of magnesium phosphide? It's a particle-particle problem. Let's begin by writing 9.3 times 10 to the 25th formula units of Mg3P2, the number, unit, and label. I'll get my 3 parentheses ready so I can see the target. We're counting atoms of magnesium. Now, magnesium phosphide is a compound hooked by charges +2 and a -3. Its correct vocabulary word is indeed a formula unit, metal to nonmetal. In our first conversion, we know that 1 mole of magnesium phosphide would contain an Avogadro's number, 6.02 times 10 to the 23rd formula units of our compound called magnesium phosphide. In the heart of our problem, we want to know magnesium. Its coefficient is a 3. It places on top. Starting from the given amount, its coefficient is a 1 mole of Mg3P2. Step 1, cancel formula units. Step 2, cancel moles of magnesium phosphide. We're at moles of magnesium. We'd like to convert out to atoms of magnesium. We know that there's an Avogadro's number of atoms in every 1 mole of magnesium. Avogadro gets placed on the top over 1 mole. The reason this vocabulary word, atoms, magnesium is just a symbol of an element. Its building block are called atoms. The compound's building block are known as formula units. You can count anything and have a mole's worth, Avogadro's number. With this particular problem, I'm noticing step 1 and step 3 cancel each other. If we divide by Avogadro and later multiply by Avogadro, we can simplify the math by crossing off step 1, step 3. I will hit 9.3 E25 times 3. And my answer, 2.79 times 10 to the 26th atoms of magnesium.